Hello, dear students. I prepared this material because I saw that many of you have problems with the dot representation, the geometrical structure of molecules, and also with the solubility according with these theories. Well, in chemistry and physics, the valence electrons are very important because they are the electrons in the outermost shell of an atom, and they are the ones that participate in the formation of a chemical bond. For example, in this case, carbon has 1, 2, 3, 4 valence electrons, and hydrogen has only one. When they 4 atoms of hydrogen join 1 atom of carbon, they make 4 bonds. They share these electrons. In the case of hydrogen, they make a duplet in each case, and in the case of carbon, this carbon get the octet. All the atoms try to get a electrons around it. That is what we call the octet rule, because it's the noble gas representation that is the most stable structure for an atom. In the case of hydrogen, that is in period 1, group 1, and has only 1 electron, hydrogen is only allowed to get 2 electrons as much, so it gets the duplet rule. According with the position in the periodic table, you can know, or you can determine the number of valence electrons for every atom. All the elements in group 1 has 1 valence electron, in group 2, 2 valence electrons, and so on. In the case of helium, helium has only 2 valence electrons, even though it is in group 8A, because helium is in period 1 and is allowed to have 2 electrons as much. So here you have the dot representation for some of the atoms in the periodic table. Well, how can you represent a molecule using the Lewis structure? First, you have to calculate the total number of valence electrons in a compound. You have to choose the central atom and place the remaining atoms symmetrically around the central atom. Place 1 electron pair or a line between each pair of bonded atoms. And you complete the octet for each atom or the duplet for hydrogen by placing the remaining valence electrons as electrons pairs around the atoms. If there are not enough electrons for you have to form multiple bonds. Well, let's see some examples, and this way you will understand better. Here we have the case of O2. Well, you have 2 atoms of oxygen. You join them using a pair of electrons. And you say, well, this atom has 6 electrons, valence electrons, and this 6. Then you have a total of 12 valence electrons. You begin representing the electrons around 1 oxygen In this case, you have 8 electrons, but you have 4 more. Then you put the 4 electrons around the other oxygen. Now this oxygen get the octet rule, but this doesn't. What you have to do in order to make the octet rule for both atoms? Well, you make a double bond this way, and now you have A electrons for this oxygen and A electrons for this oxygen. And this is a stable Lewis structure. What happened in the case of the bond between silicon and oxygen? Silicon has 4 valence electrons and oxygen 6. Then you have a total of 10 valence electrons. You begin bonding both atoms using 2 dots in between or a dot. And later you begin completing the octet rule for one of the atom. Then until this moment you have 8 valence electrons, but you have 2 more. Then you put the 2 electrons here. And now you have the octet rule for this oxygen, but you have only 4 electrons around this silicon, and this silicon is demanding the A electrons to get the octet rule too. The only way you can get the octet rule for both atoms is by making a triple bond this way. Now you have A electrons for silicon and A electrons for oxygen, and this is the stable Lewis structure for this molecule. Let's see another example. You can stop the video at any time and see the explanation again in order to understand it. The best way is that you try to do it by yourself in your notebook. Let's see, in this case, you have 1 hydrogen and 2 oxygen. Then you put 1 hydrogen and 1 oxygen and 1 oxygen. You choose this oxygen as central atom. And you know that this hydrogen has 2 valence electrons, 6 this oxygen, and 6 is 1. Then you have a total of 14 valence electrons. You begin putting 2 electrons in between, and then you complete the octet rule for one of the oxygen. Now you have 8 and 2, 8 electrons. Then you have 6 electrons more. Then you put sorry, here is not 14, it's 10. Is 6 and 6, 12, 14. Yes, I am right. Then 8 and 2 are 10. Then you put the rest 4 electrons to get the 14 ones around this oxygen. And now you see that this oxygen has the octet rule. This also have the octet rule. And what is the problem? That you have an extra electron here because it's an anion. And how can you represent this electron in the case of an ion? Well, you put it into brackets and you represent the charge of the ion outside. This is the stable Lewis structure for this ion. In the case of chlorine, bromine, iodine, all the elements, fluorine, in group 7, well, you have 7 valence electrons for every atom. You have a total of 14 valence electrons. You join the 2 atoms by two electrons. you complete the octet for one of them. Now you have 8 electrons, but you have 6 more to get the total 14 electrons represented. Then you put the 6 here. And now you can see that every atom get the octet rule. So this is the stable Lewis structure for any kind of halogen. In this molecule, you have 1 carbon, 2 oxygen, and 1 oxygen. 2 hydrogen and 1 oxygen. Then you put the central atom is carbon, you put 1 oxygen, 1 hydrogen, you put 2 electrons in between, and now you begin, you have 6 electrons, you have 6 more to share, then you complete 1, 2, 3, 4, 5, 6. Now you have the 12 electrons represented around the atoms. And look at this. Now this atom has the octet rule, but this carbon has not the octet rule. How can you get the octet rule for carbon? By making a double bond this way. Now you have A electrons, 2 electrons for hydrogen and 2 electrons for hydrogen. And this is a stable Lewis structure for this molecule. You can stop the video and watch it again. In the case of carbon dioxide, you have 1 atom of carbon and 2 of oxygen. You have 6, 6, and 4 is 16 electrons. Then you represent the 16 electrons by what you can see. This oxygen and this oxygen get the octet rule, but not this carbon. The only way is by making a double bond between this carbon and this oxygen, and this carbon and this oxygen. Now, this carbon get the octet rule, and so the oxygen and this oxygen. The double bonds, in this case, make a stable the molecule, and this is the structure that is assumed. Well, the valence shell electron pair repulsion, VSEPR theory, helps us to understand and predict the geometry or the shape of the molecules or the ions. This theory is based on the idea that the electron pairs repel each other, whether they are in chemical bonds or lone pairs. So, let's see what we have to do. For example, in this molecule, we have 2 groups of electrons. Here you have 2 groups of electrons, and you have no lone pairs. So the molecule is supposed to be linear. Because linear is the geometry where you can have apart this atom from this atom. Look, in this case, you have 3 groups. Then the best way you can separate as much as possible is making a trigonal planar structure. In this case, that is a tetrahedral. You have to make a bond between atoms of 109.5 degrees to get the atoms in the edges separated as much as possible because of the repulsions of the electrons pair. Well, these are the cases where you have no lone pairs. But look at this. Here you have three groups of electrons, and you have one of the groups is a lone pair. Then it is not trigonal planar, it is bent. In the case that of the four electron groups of electrons around the central atom, and you have one lone pair, then the structure is trigonal pyramidal. It's like a pyramid, but you have this group of non-bond or lone pairs electrons. In the case of four groups of electrons around the central atom, but two of them are lone pairs, the best structure is the band. Then you can use this table, and according with the number of electron pairs around the central atom and the lone pairs, you can choose the best structure to represent every molecule. In the case of beryllium fluoride, you have two groups of electrons, and you have no lone pairs, so the molecule is linear, and the bond angle is 180 degrees. What happened here in boron trifluoride? Well, you have 1, 2, 3 groups of electrons, and they are bound. So the structure is trigonal planar, and the bond angle is 120 degrees. In the case of methane, you have 1, 2, 3, 4 groups of electrons around the central atom, and no lone pairs. So the best structure to represent the methane or CH4 is using the tetrahedral model. And the bond angle is 104.5 degrees. Let's see these three cases. In these three cases, you have 1, 2, 3, 1, 2, 3, 1, 2, 3 groups of electrons. In the first case, you have no lone pairs, so the molecular shape is trigonal planar. In the second case, you don't have lone pairs. So you have also the molecular shape that is trigonal planar. In the third case, you have a lone pair of electrons. So it is not trigonal, it is bent. Look, sulfur dioxide, SO2, has a bent structure or V shape. In this table, you can observe the electronegativity of every atom. As you can see, fluorine is the most electronegative element, followed by oxygen and by nitrogen. Don't forget these three elements are the most electronegative, because we are going to use this later to explain the hydrogen bonds. These three atoms are the only ones that can make hydrogen bonds when they are bonded to hydrogen. As you can see, the francium is the less electronegative element, the electronegativity is 0.7 in this case. According with the color, you can see the electronegativity groups of the different atoms. You can use this table to establish when the bonds between two atoms could be covalent, polar covalent, or ionic. If the difference of electronegativity between two atoms is 0 or less than 0.4, you say that the bond between these two atoms is covalent. In the case that the difference of electronegativity between the two atoms is between 0.4 and less than 2, then you can say that the molecule is covalent but polar. Then it's polar covalent, like the case of chlorine with hydrogen. Remember, here I am only determining the character of the bond between two atoms, not a molecule, okay? In the case of the ionic bonds, the difference of electronegativity between the two atoms must be higher than 2 or higher. So using this table and getting the difference of electronegativity, I can get the type of bond that we can get between two atoms. It doesn't mean that the molecule at all is covalent or ionic or whatever. Let's see, in order to say that the molecule is polar or non-polar, we have to make an analysis of what we call the dipole moment. Well, if you analyze this carbon and this oxygen, you can see that oxygen is more electronegativity or electronegative than carbon. So you make this symbol to represent the dipole moment between these two atoms. The same thing happened in this molecule, but because carbon dioxide is linear and the dipoles are equals and in different directions, you cancel out both dipoles, and the result of this molecule is that is non-polar. Then the net dipole moment is very important to see if the molecule is polar or no, because look at this. You have two bonds and both are polar, but that molecule at all is not polar because of a structure of the molecule. Because these two dipole moments are equal, but they are opposite, they cancel out. So the total molecule is non-polar. Let's see. Well, look at this. Here we have water. Yeah, we have a dipole here between hydrogen and oxygen, they are equal, but in this case, because of the shape of the molecule, the net dipole moment is different from zero, and water is a molecular, is a polar molecule, while carbon dioxide is known. What is the difference? Oh, because even though you are in presence of two bonds that are polar, the structure or the geometric structure of the molecule makes this molecule non-polar while water is polar. Look at this. In this case, you have four bonds, carbon and chlorine. Chlorine is more electronegative than carbon. So you have to represent the dipole in direction of chlorine. And here another one, and here another one, and here another one. But because of the structure of this molecule, these dipoles are canceled out, and the net dipole moment of this molecule is zero. So carbon tetrachloride is non-polar, even though every single bond is polar. Then the geometrical structure of the molecule is very important to say whether the molecule is polar or no. You know this rule, like dissolve like. What is the meaning? Polar dissolve polar. For example, ethanol is dissolved in water. Non-polar dissolve non-polar. For example, hexane can be dissolved in oil. But non-polar will not dissolve polar. So oil that is non-polar cannot be dissolved in water that is polar. This is a general rule, but you cannot stop into here, say, well, if this dissolves in this, and I know that water is polar, then the other one is polar. Not only this can be used in an explanation, because it's incomplete. So you have to explain also the hydrogen bonds to explain solubilities. What is a hydrogen bond? Well, here we have two water molecules. You know that water itself is a dipole, where you have a delta negative charge to the oxygen and a delta positive charge to the hydrogens. Then there is an extra attraction between molecules. This attraction is a type of interaction between molecules that makes this attraction stronger between two molecules in the case that they make a hydrogen bond. That's why water boils at 100 Celsius degrees, because in order to make water vapor, you have to destroy, you need energy, extra energy to break down these hydrogen bonds. So even though water has a simple structure because of the hydrogen bonds, we need more energy, and water is at a room temperature a liquid, while CO2 that has a similar structure is a gas, because carbon dioxide is non-polar, and also cannot make hydrogen bonds. Hydrogen bonds are only possible, and let me show you here, when you have nitrogen with hydrogen, molecules that contain this bond can get hydrogen bonds. Also, oxygen and hydrogen, like in water, or this bond, fluorine and hydrogen. Remember that fluorine, oxygen, and nitrogen are the most electronegative atoms in the periodic table. So the presence of hydrogen bonds is also important to express when a substance can be dissolved in water or not. For example, in the case of the alcohols, well, alcohols have an OH group. Alcohols have an OH group. This is polar and can make hydrogen bonds with water. That's why alcohols in general, in special the ones with lower molecular mass or weight, can be dissolved in water easier than other compounds that have not hydrogen bonds. For example, water can dissolve ammonia better because they are polar and because they have an attraction between them. The same thing here between two molecules of hydrogen fluoride. They can make hydrogen bonds, so they can be dissolved better than if you don't have hydrogen bonds. Look at this, water and water makes hydrogen bonds. Water and nitrogen and hydrogen, the hydrogen of the water and the nitrogen of the ammonia can make hydrogen bonds, and that's why ammonia can be dissolved in water easier. And the same thing between an alcohol and water, or the case of hydrogen fluoride. Well, I think that now you have a better idea of what or how to explain and answer for these questions. Well, that's all. See you soon. If you have more questions, don't hesitate to ask me. I am always here. If you want to ask me for a meeting by Zoom, and I will be there at any time. Bye.